Hello, calculus students and seekers of truth. In this video, we continue our study of infinite series, and I should qualify that we're dealing with infinite geometric series only right now. There are other series that we're not quite prepared yet to handle. And we know that if a series is geometric with the first term of A and a common ratio of R, then the sum of the first n terms, S of n, is going to follow this formula. And so what happens if n is infinite? Well, that's not too difficult, at least in theory, to calculate based on what we know so far. If n is infinite, then the infinite sum, we can just take the limit. We can ask ourselves, what happens to S sub n as n approaches infinity? Like so many other things that we do, that's what we're going to do. We're going to ask that question. Okay, so that's all there really is to this part of it. We're going to go back to this idea just a little, in just a few moments after we try out some examples. So here are some examples. I have k is equal to 1 to infinity. That's the sum that we're going to add up. And this is the term that we're going to, this is the calculation for each of the terms. So I think it's helpful if we just expand this a little bit. And, the first term, if k is equal to 1, then you got 5 times 1.01. Then the next term, you're going to have 5 times 1.01 squared. Then the term after that, you're going to get 5 times 1.01 cubed and onwards. And you can see here already pretty clearly that this series is going to diverge because you're adding a number each time. Even if you were to add 5, even if you were just to add 5 infinitely many times, you're going to get an infinitely large value, or a value that grows forever without bounds. Just for a little bit of practice, we could use what we know here. We're going to use the limit notation. Right? So we're going to use the limit as k approaches infinity of the formula that we're practicing how to use. A here is 5. This is 1 minus r. The ratio is 1.01 to the kth power. All of this divided by 1 minus 1.01. So the numerator is going to be 5, 1 minus 1.01 to the k. All of this divided by negative 0.1. Right? Now you can see this part up here, this section 1.01 to the k, as k goes towards infinity. Uh-oh, I forgot to keep my limits in place here. Let's see, squeeze this in here. The limit as k approaches infinity. Right, so this part right here, that's the all-important part. 1.01 raised to an enormously large value is going to give you another enormously large value. And so this is going to approach infinity, or it's going to get closer and closer to infinity ever so much more. So we can say that this series is going to diverge. Just going to keep getting bigger and bigger and bigger forever. All right, let's look at the next example. Our first term is going to be 80 times 2/3 to the first power plus 80 times 2/3 squared plus 80 times 2/3 to the third. I think you get the idea from here. And so we know now in this case that R is 2/3 and A is 80. So if we use the formula that we're familiar with, we're going to take the limit as k approaches infinity of the first term, 80 times 1 minus the common ratio, 2/3. I'm just going to put parentheses here, raised to the kth power. And then all of that divided by 1 minus 2/3. So this will give us the limit as k approaches infinity. In the numerator, we have 80. 1 minus, and in the denominator, it's going to be 1/3. Okay. And I haven't completed this part yet, but you see that if you have a fraction, a proper fraction, and you raise it to an infinite power, so you're going to have 2/3 times 2/3 times 2/3 times 2/3, that number is going to get smaller and smaller and smaller and smaller. And so what you're going to end up here with is 0 in that spot. And so when we try to figure out this final sum, it's going to be 80 times 1 divided by 1/3. That's the same thing as multiplying by 3. So that will give you 240. Okay? So this is saying the more terms you add, you're not going to quite get to 240, but you're going to get really, really, really close to 240. In other words, this series will grow. It will continue to grow forever, but it will be bounded at 240, or it will get closer and closer to 240. And so these two examples here, I hope, give you some sense of how to determine if a geometric series is going to converge or diverge. And the key here has to do with this part, the part that I circled up here, and the part that I circled down here. So for a geometric series, you see that if R is a proper fraction, then the geometric series, the infinite geometric series, is going to converge. And if R is an improper fraction, or it's some number greater than 1, then the geometric series is going to diverge. Okay, so now we can make some sort of broad statement about whether a series is going to converge or diverge. Okay, so first of all, for any series at all, we can say if, this is kind of rule number 1, if the sequence does not approach 0, then the series will diverge. Okay? And you should think about why this is true. You can try out some examples on your own. I'll give you kind of an intuitive understanding of this. If you're adding a list of numbers, even if you're adding a very small list of number, even if you're adding 0.1, 0.1, 0.1, but if you're adding this infinitely many times, eventually this list is going to get very, very large. This sum, is going to get very, very, very large. Okay, so if these numbers don't get closer and closer to 0, the series will definitely diverge. Okay? And this is true of all series, not just geometric ones. All series, if the sequence is not getting, if the terms is not approaching 0, then the series is definitely going to diverge. Okay? I want to point out that the inverse of this statement is not necessarily true. Okay, so if the sequence does approach 0, we're not really sure yet. Okay? 2, for geometric series, we can tell this really, really quickly. For geometric series, remember that the sum of a geometric series, an infinite sum of a geometric series, is equal to A, that's the first term, times 1 minus r to the n. All of this over 1 minus r. Okay? So when we take this limit as n approaches infinity, there's two scenarios that we can consider. If r is a proper fraction, and it's okay for it to be negative. Okay, so if r is between -1 and +1, then the series will converge, as we saw above. And it will converge because this part right here, r to the n, will approach 0. It will shrink down to 0. So not only do we know that it converges, we know that it converges to a over 1 minus r. Just like this incredibly simple and elegant formula for adding up an infinite list of numbers. Okay, so we call this geometric series case A if R is a proper fraction, and otherwise, if R is not between -1 and 1, so we can say if the absolute value of R is greater than or equal to 1, then the series will definitely diverge. So there's so much more that we have to learn here about series, but this is a good first step forward. We say that we know something pretty good about geometric series. If we can identify that it's a geometric series, then we can tell really quickly whether it's going to converge or diverge, and we can tell what it will converge to. And otherwise, and for all the other cases, we can only tell if it's going to diverge. We're not sure if it's going to converge. It's kind of hard to tell for sure if a series is going to converge. Okay, so we have like a divergence test here, and then we have a convergent and divergent test for specifically geometric series. So here ends our lesson review introduction into in the world of infinite series. And again, all of this and all of what we're going to learn going forward is a set of tools that we're going to use to analyze and handle and understand the Taylor series that we learned from before. Okay, so I just want you to keep that in the back of your mind. These are tools, techniques that we're going to learn, and the real goal is to understand Taylor series, Taylor polynomials. As always, thank you for watching. Ask for help if you need it, and have a wonderful day.